Well, welcome back to our course on systems engineering. For this chapter, we're going to be talking about needs analysis. And just to give some perspective, this is the first in several chapters that are talking about concept development. So we had 4 lectures that were talking about the foundations, and it really sets a stage for what we're going to be talking about in part 2, part 3, and part 4. And so we'll see how that works, but let's just go ahead and get into some of the details here. And so this is the front end work. And so we'll be leveraging some of the figures we've seen before with this lecture. So first of all, for originating a new system, the primary objective of the needs analysis phase of the system lifecycle is to show clearly and convincingly that a valid operational need or potential market exists for a new system or a major upgrade to an existing system, and that there is a feasible approach to fulfill the need at an affordable cost and within an acceptable level of risk. It answers the question of why a new system is needed and shows that such a system offers a sufficient improvement in capability to warrant the effort to bring it into being. This is achieved in part by devising at least one conceptual system that can be shown to be functionally capable of fulfilling the perceived need and describing in a sufficient detail to persuade decision makers that it is technically feasible and can be developed and produced at an acceptable cost. In short, this whole process must produce persuasive and defensible arguments that support the stated need and create a quote vision of success in the minds of those responsible. For authorizing the start of a new system development, so that's the focus there. Okay, what about the place of the needs analysis phase in the system lifecycle? The exact beginning of the active development of a new system is often difficult to identify. This is because the earliest activities in the origin of a new system are usually exploratory and informal in nature without a designated organizational structure, specified objectives, or established timelines. Rather, the activities seek to determine whether or not a dedicated effort would be warranted based on an assessment of valid needs for a new system and a feasible technological approach to its implementation. The existence of a discrete phase corresponding to that defined as the needs analysis is something that we're getting into here, and also in another chapter. So we're just beginning this process. So and we'll come back to that again. And the needs analysis, in another chapter and lecture, is more characteristics of the needs-driven systems development than of those of a technology-driven. In defense systems, for example, quote, material solution analysis, which is seen in the DoD lifecycle, which we've already talked about, is a required prerequisite activity for the official creation of a specific item in the budget for the forthcoming fiscal year, thereby allocating funds for the initiation of a new system project. Within this activity, a need determination task produces an initial capability description, ICD, which attests to the validity of the system objective or need and gives evidence that meeting the stated objectives will yield significant operational gains that is feasible of realization. Its completion culminates in the first official milestone of the defense acquisition cycle. Other non-defense systems may also have needs that may be more community-driven, such as requiring a new freeway, mass transit system in the case of transportation, or human health issues, such as required integrated healthcare services to address multiple health hazards, and also thinking of NASA looking to its science community to help out determining what it needs to invest in for future missions. Okay, now when we're getting into the details here, we're looking at this illustration here. And so this is a blow up of what we saw in the last couple of lectures, the last couple of chapters. And this is focusing on the needs analysis. In a technology-driven system development, typical of new commercial systems, that the needs analysis phase is considered to be part of the conceptual development stage. We saw this in a previous figure in chapter 3. An example would be the telecommunication industry, where new products and capabilities from the competition will drive newer systems development to capture market share. However, in this case too, there must be similar activities such as market analysis, assessment of the competitive products, and assessment of deficiency of the current system relative to the proposed new system that establish a bona fide need, that is potential market for a product that will be the object of the development. Accordingly, the discussion to follow will not distinguish between needs-driven and technology-driven system developments, except where specifically noted. The place of the needs analysis phase in the system lifecycle is illustrated in this figure here. So it's a blow up of what we've seen earlier just for this particular part. And its inputs are seen to be operational deficiencies and or technological opportunities. Its outputs to the following phase, concept exploration, are an estimate of system operational effectiveness that specify what results a new system should achieve to meet the identified need together with system capabilities. The output of various operational analyses and system studies, which provide evidence that an affordable system capability of meeting the effectiveness target is feasible. As discussed above and depicted in the figure, the impetus for the initiation of a new system development generally comes from one of multiple sources. One, the perception of a serious deficiency in a current system designed to meet an important operational need, so it's need-driven. Two, an idea triggered by technological development whose application promises a major advance over available systems and satisfying a need. And so that would be a technology-driven reason. Or three, for example, an emergent global healthcare need that is rapidly spreading throughout the entire world. Or four, policy changes to perform daily routines, such as increasing use of autonomous vehicles or smart grids to provide additional capability. Any of these may lead to investigations and analysis that eventually culminate in a program to develop a new system. Quite often, several factors contribute to the final decision. Okay, what about examples of new systems needs? The automotive industry is a prime example where changing conditions have forced the needs for system improvements. Beginning in the 1960s, the government made laws that required manufacturers to make substantial improvement in fuel economy, safety, and pollution control. Almost overnight, existing automobile designs were rendered obsolete. These regulations continue to pose a major challenge to the automotive industry because the required technology, they require technically difficult trade-offs in the development of many new components and materials. While the government gave manufacturers a number of years to phase in these improvements, the need for innovative design approaches and new components was urgent. In this example, the need for change continues to be triggered by legislative action based on the needs of a society as a whole. Examples of technology-driven new systems are application of space technology to meet important public and military needs. Here, the development of a range of advanced devices such as powerful propulsion systems, lightweight materials, and compact electronics makes the engineering of reliable and affordable spacecraft a practical reality. In recent years, satellite manufacturers have become competitive and often develop superior platforms for communication relays, navigation, such as the Global Positioning System or GPS, weather surveillance, and a host of surveying and scientific instruments. A more pervasive example of technology-driven system developments is the application of computer technology to the automation of a wide range of commercial and military systems. Information and network systems in particular, for example, banking, ticketing, routing, and inventory, have been drastically altered by computerization. System obsolescence in these cases has come not from recognized deficiencies, but rather from opportunities to apply rapidly advancing technology to enhance system capabilities, reduce cost, and improve competitive position. Healthcare systems have increased the use of technology to provide additional monitoring of patients' vitals, yet still require the human, that is a nurse or a healthcare provider, to observe, process, and take action based on the displays, sometimes by remote communications. We also have external events, as will be seen later in this discussion in this lecture and the section in the textbooks that follows this. Analysis of needs goes on more or less continuously in most major missions or product areas. However, external events often precipitate intensification and focusing of the process. This results in the formulation of a new operational requirement. In the defense area, this may be finding of a new potential threat, a local conflict that exposes the deficiency in a system, or a major technological opportunity uncovered in a continuing program of concept exploration, or a major deficiency uncovered in a periodic operational testing outcome. In the civil products area, a triggering event might be a sudden shift in customer demand or a technological change, such as a discovery of a radically new product or opportunity to automate a labor-intensive process. In terms of competitive issues, going from a perceived need to an initiation of a development program requires more than a statement of that need. Regardless of the source of the funding, whether it's government or private, there is likely to be competition for the resources necessary to demonstrate a bona fide need. In the case of the military, it is not unusual for competition to come from another department of service. For example, should maritime superiority be primarily a domain of the surface or the air navy, or a combination of the two? Should clean air be achieved by restrictions in the automotive engine combustion process or the chemical composition of the fuel? The answer to these types of questions can have a major impact on the direction of any resulting development. For these reasons, strong competition can be expected from many sectors when it is publicly known that a new system development is under consideration. The task of sorting out these possibilities for further consideration is a major system engineering responsibility. Well, next, let's think about the needs analysis phase, the status of the system materializations at the needs analysis phase, and give some context here, thinking more deeply from the material from our textbooks. So for the design materialization status, as described elsewhere in the textbook, the phases of the system development process can be considered as steps in which the system gradually materializes, that is, progresses from a general concept to a complex assembly of hardware and software that performs an operational function. In this initial phase of the system lifecycle, this process of materialization has only just started. Its status is depicted here in the table. The focus of attention in this phase is on the system operational objectives and goes no deeper than the subsystem level. At that level, the activities is listed as quote, visualize rather than definition or design. The term visualize is used here and elsewhere in the textbook and also the lectures in its normal sense of forming a mental image or vision, implying a conceptual rather than a material view of the subject. It is at this level of generality that most designs first originate, drawing on analogies from existing system elements. So the table oversimplifies a representation of the evolving state of a system by implying that all of its elements begin as wholly conceptual and evolving as a uniform rate throughout the development. This is very seldom, if ever, the case in practice. To take an extreme example, a new system based on rectifying a major deficiency in one of the subsystems of a predecessor may well retain the majority of other subsystems with little change, except perhaps in the selection of production parts. Such a new system would start out with many of the subsystems well advanced in materialization status, and with very few, if any, in a conceptual status. Similarly, in a new system, a new system is technology driven, as when innovative technical approach promises a major operational advantage. It is likely that parts of the system not directly involved in the new technology will be based on existing system components. Thus, the materialization status of the system in both examples will not be uniform across its parts, but will differ for each part as a function of its derivation. However, the general principle illustrated in the table is nevertheless valuable for the insight it provides into the system development process. In terms of applying the system engineering method in needs and requirements analysis, as the initial phase in the system development cycle, the needs analysis phase is inherently different from most of the succeeding phases. There being no preceding phase, the inputs come from the different sources, especially depending on whether the development is needs-driven or technology-driven, and on whether the sponsor is the government or a commercial company. Nevertheless, the activities during the needs analysis phase can be usefully discussed in terms of 4 basic steps of the system engineering method described in another chapter with appropriate adaptation. These activities are summarized below. The generic names of the individual steps as used elsewhere are listed here, and we'll be discussing them. So let's go ahead and talk about them one at a time. So for operational analysis or requirements analysis, the typical activities include analyzing projected needs for a new system, either in terms of serious deficiency of current systems or the potential of greatly superior performance or lower cost by applying application of new technology. Understanding the value of fulfilling the projected needs by extrapolating over the useful life of the new system, and defining quantitative operational objectives and the concept of operation. The general product of this activity are a list of operational objectives and system capabilities. Next, we have functional analysis or functional definition, and typical activities here are translating operational objectives into functions that must be performed, and allocating functions to subsystems by defining functions, interactions, and organizing them into a modular configuration. The general product of this activity is a list of initial functional requirements. Next, we have the feasibility definition or the physical definition. And this typically includes visualizing the physical nature of subsystems conceived to perform the needed system functions, and defining a feasible concept in terms of capability and estimated cost by varying, that is, trade-off, the implementation approaches as necessary. The general product of this activity is a list of initial physical requirements. Then we have the needs validation or the design validation, and the typical activities in this are the designing or adapting an effectiveness model, either an analytical or simulation model with operational scenarios, including economics, and economics would consist of cost, market, etc. Factors. There's also the defining validation criteria. There's the demonstrating the cost effectiveness of the postulated system concept after suitable adjustment and iteration. And finally, formulating the case for an investment in the development of a new system to meet the projected need. The general products of this activity are a list of operational validation criteria. Given a successful outcome of the needs analysis process, it is necessary to translate the operational objectives into a formal and quantitative set of operational requirements. Thus, this phase produces 4 primary products: operational requirements, which refers largely to the mission and purpose of the system. The set of operational requirements will describe and communicate the end state of the world after the system is deployed and operated. Thus, these type of requirements are broad and describe the overall objectives of the system. All references relate to the system as a whole. Some organizations refer to these requirements as capability requirements or simply required capability. Next, there's the functional requirements, which refer largely to what the system should do. These requirements should be action-oriented and describe the tasks or activities the system performs during its operation. Within this phase, they refer to the system as a whole, but they should be largely quantitative. These will be significantly refined in the next 2 phases. Then we have the performance requirements, which refer largely to how well the system should perform its requirements and affect its environment. In many cases, these requirements correspond to the 2 types above and provides minimum numerical thresholds. These requirements are almost always objective and quantitative, although exceptions occur. So these will be significantly refined in the next 2 phases. Then we have the physical requirements, which refer to the characteristics and attributes of the physical system and the physical constraints placed upon the system design. These may include appearance, general characteristics, as well as volume, weight, power, material, and external interface constraints to which the system must adhere. Many organizations do not have a special name for these and refer to them simply as constraints or even system requirements. These will be significantly refined in the next 2 phases. Well, we looked at this figure before, the needs analysis phase flow diagram, and we'll be now giving a little bit more specific context for this part of the conceptual development phase. For new start systems, the first iteration through the needs and requirement analysis phase results in a set of operational requirements that are rather broad and not completely defined. The requirements like document that emerges from the needs analysis is formally known as the ICD. This term is also used as a generic description of capabilities desired. In either case, the ICD document contains a broad description of the system concept needed and focuses on operational or capability requirements. Only top-level functional, performance, and physical requirements are included. Later documents will provide details to this initial list. The elements of the system engineering method as applied to the needs analysis phase described below are shown in the figure here with appropriate modifications for the activities in this phase. The rectangular block represents the 4 basic steps, and the principal activities are shown as circles with the arrows denoting the information flow. The inputs at the top of the diagram are operational deficiencies and technological opportunities. Deficiencies in current systems due to obsolescence or other causes are need-driven. Technological opportunities resulting from an advance in technology that offers a potential major increase in performance or decrease in cost of a marketable system or technology drivers. In the latter case, there must be a projected concept of operation for the application of the new technology. The 2 middle steps are concerned with determining if there is at least one possible concept that is likely to be feasible at an affordable cost and acceptable risk. The validation step completes the above analysis and also seeks to validate the significance of the need being addressed in terms of whether or not it's likely to be worth the investment in developing a new system. Each of these 4 steps is further detailed in the succeeding sections of what we're covering in this lecture and the book chapter that corresponds to it. So for user interactions, users are needed for consultation on whether the needs are valid and to prioritize the needs, whether they are needed or required new needs. If they are needed or are required new needs. This is typically based on experience with the legacy system and identification of deficiencies based on changes in mission or threats. Users may be consulted in a variety of methods. Interviews allow a means of follow-up questions, while surveys can reach a larger range of users. A wide variety of users should be consulted to capture the needs, as a variety of perspectives can uncover many more needs of the system concept before it comes to market. Then we have customer satisfaction. Customer satisfaction is a continual process to determine if the system is performing satisfactorily. Often comments from the customer may uncover different features that could be valuable for the future iteration of systems. We want to pay attention to the customer as they describe what is liked and is not liked. A variety of information can be gained, such as operating instructions / procedures may not be clear as the engineers design it. Customers may operate the system in an environment not originally designed for. Human factors may prompt a redesign of the system to accommodate a greater range of customers. All of these comments are valuable to the systems engineer to understand what could be improved for the future system and supporting infrastructure. Note that model-based system engineering support non-textual requirements in the form of constraints, measures of effectiveness, MOE that is, and other system properties. As the discipline matures, it is likely that some hybrid approach, including traditional textual requirements, property-based requirements, and collections of other system elements, say, for example, a well-informed state machine that includes rigorous definition of state transitions and behavior, will be used to communicate intent to stakeholders and those involved in the system engineering process. Next, we want to be talking about system thinking. When determining the need for a new system or a fact while conducting each phase of the system development, the system engineer should adopt the role of systems thinking in leading and guiding teams in the development of complex and highly integrated systems. The key to understanding the need and design of the system is to consider the system in a holistic perspective. The full life cycle of the system takes into account the stakeholders' expectations, the system's users, the advancing rate of technology, the operational and physical environment, and the social and policy influences. System thinking should be a part for each contributor of the system development. The practicing Systems engineer is a quintessential systems thinker. System thinking is a set of habits or practices within a structure that is based on the principle that the parts of a system are best understood within the framework of relationship of the parts with each other and with other systems rather than in isolation. From the design through production, the focus is on whether you are developing the right thing, that is, our customers' requirements being met, our users satisfied with the system performance, our interactions with other systems compatible, and implications of change understood. Are the system dynamics expected and smooth, and are outcomes economically acceptable and sound? A whole lot of things, in other words. So this way of thinking is continually engaged in validating and validation and verification of the aspects of the system. All domains that touch the system have needs met, and everyone buys into the design. A system thinker understands and sees the big picture, recognizes interconnections, and can view multiple perspectives. At the same time, the system thinker is creative and not stuck on details. Effectively, they're able to, quote, see the future. Systems thinking must also anticipate unexpected behavior in complex systems when the subsystems are integrated or encounter new environments. This emergent behavior of unintended consequences can be avoided by thinking in advance how the system would perform and accommodate appropriate design and development changes. Hence, you are encouraged to think about problems and solutions with an eye towards a long view for the whole system. Not only can requirements change, but also the world view of concepts and solutions may change. Technical and societal advances create new challenges and opportunities that need to be incorporated into the system design. While successful revolutionary products are welcome, single-purpose designs may not meet future trends. Strong leaders design robust and resilient systems and communicate effectively to the stakeholders and the design team. A system behavior or response to sensor input is dynamic due to the interactions and connections that cause a feedback loop between output and input to a subsystem. Systems thinking identifies the operational environment, especially in social contexts, for threats that directly or indirectly will influence performance. The thinking must take on a temporal perspective, recognizing initial design concepts may need to be broader than limited initial needs and requirements, and that over time, more robust approaches may be needed. The system engineer, when thinking holistically, considers the world as a system of systems that are interconnected and interact to influence each other and the external environment. System thinking can then be used to analyze the different factors in the system role within the operational environment, and how system engineers can identify relationships and evaluate how the system plays a role within the larger picture. So the textbook has a reference to Kaiser and Mackley that presents an overview of the different perspectives that one can view systems in a holistic perspective. I recommend that you look at the textbook for that reference. Many are principles that are used in system engineering, and they should be applied to understand how the system concept can operate within the larger picture to include the operational environment. These are operational, that is, applying use cases and concepts of operation to identify the system, how the system will work in the environment. Functional, dealing with defining what functions are needed to operate. Big picture, which is viewing the system in the context diagram approach to identify other relevant actors and the interdependencies between them. Structural, considering the system architecture for internal and external connections. Generic, looking for similar properties from similar systems and inheriting them. Continuum, how do failures of other interdependent systems affect our system? Temporal, evaluating system behavior as a function of time, which may depend on interdependency. Quantitative, how to develop the mathematical relationships in the model and simulation. And scientific, looking at how to formulate and test the hypotheses. So what we're going to be talking about next in the section below will show system thinking occurring during the system engineering process. So let's introduce an example of system thinking. Common system thinking methods and tools include system dynamics and causal loop diagrams. These should show the relationship between various contributors, and the system can show the effects of changing relationships and the behavior of the system or systems over time on the inputs and output change. Other popular tools include agent-based modeling to define the attributes and behavior of a contributor and how it operates depending on the external environment changes. These approaches can then provide guidance on how the system will be expected to operate, determining what type of relationships are required, and also to help define the required behavior based on the context of the system. So in terms of an example of how system thinking is applied is to show how the problem can be described, identifying the relevant actors and relationships, and this can then aid in defining desired behaviors and performance. Consider the social system for immunization rates in Kerala, India, to understand coverage and overall household trust in immunization. And so there's a reference, Barksey, that's listed in the textbook that I would refer you to. The first order effects focus on the household immunization influenced by both private and public doctors, as well as health field workers. When a polio campaign was introduced as part of the Global Polio Eradication Initiative, a separate series of causal loop diagrams showing the second and third order effects discovered additional sources that would either support or oppose the immunization efforts, to include alternative providers, religious leaders, academic/private doctors, media coverage, and side effects of the Japanese encephalitis vaccination in a nearby state that cause additional public debate and options on household trust. So consider next a system thinking example in the development of an advanced autonomous automobile system, or AAS. The self-driving vehicle would have more independence than those of today. The system engineer would decompose the problem into subsystems. For example, the vehicle, location sensors, sensors for detection and identification of other vehicles and objects, communication systems, control systems, vehicle riders. Then one would consider the situation awareness, the internal external environment, and the full set of surveillance capability, as well as a vehicle reaction time. But are road and weather condition effects included? Can sensors and control systems accommodate future highway effects and signals? What if a rider could override the controls and choose to exceed the speed limits? Can planned AAS subsystem be re-engineered or retrofitted to detect, identify, and react to new targets? Many other system thinking questions need to be raised to draw implications and answers that would change perceived needs and conceptual designs. Otherwise, the next AAS produce would have a short road life. Well, next, let's talk about operational analysis. Whether the projected system development is needs-driven or technology-driven, the first issue that must be addressed is the existence of a valid need that is a potential market for the new system. The development of a new system or major upgrade is likely to be very costly and will usually extend over several years. Accordingly, a decision to initiate such a development requires careful and deliberate study. Well, what about the analysis of projected needs? In the commercial sector, market studies are continuously carried out to assess the performance of existing products and the potential demand for new products. Customer reactions to product characterization are solicited. The reason for lagging sales is systematically probed. The strengths and weaknesses of competing systems and their likely future growth are analyzed. For military systems, each service has one or more systems analysis organizations whose responsibility is to maintain a current assessment of their operational capability and readiness. These organizations have access to intelligent assessments of changes in the military capability of potential adversaries that serve as inputs to the effectiveness study. In addition, periodic operational tests, such as simulated combat at sea, land operations, and so on, serve to provide evidence of potential deficiencies that may signal the need for developing a more capable system. A particularly important consideration is whether or not modification of doctrine, strategy, or tactics can better meet the needs with existing assets, thus reducing the urgency of acquiring expensive new assets. In terms of deficiencies in current systems, in virtually all cases, the need addressed by the projected new system is already being fulfilled, at least in part, by an existing system. Accordingly, one of the first steps in the needs analysis process is the detailed identification of the perceived deficiency in the current system. If the impetus for the new system is technology-driven, the current system is examined relative to the predicted characteristics achieved with their prospective technology. For commercial systems, these deficiencies may be to keep up with competition, upgrade from outdated technology, address emerging threats, or merge capabilities based on consumer demand. Since the development of successor systems or even a major upgrade of an existing system is likely to be technically complex and require years of changing work operational studies, must focus on conditions as much as 10 years in the future. This means that the system owners/user must continually extrapolate the conditions in which the system operates and reevaluate system operational effectiveness. In this sense, some form of needs analysis is being conducted throughout the life of the system. The above process is most effective when it combines accumulated test data with analysis, often using existing system simulations. This approach provides two major benefits: a consistent and accurate evaluation of system operational performance and a documented history of results, which can be used to support the formal process of needs analysis if a new development program becomes necessary. Next, let's think about obsolescence. The most prevalent single driving focus for new systems is obsolescence of existing systems. System obsolescence can occur for a number of reasons. For example, the operating environment may change, the current system may become too expensive to maintain, the parts necessary for repair may be no longer available, competition may offer a much superior product, or technology may have advanced to the point where substantial improvements are available for the same or lower cost. These examples are not necessarily independent. Combined elements of each can greatly accelerate system obsolescence. Belated recognition of obsolescence can be painful for all concerned. It can significantly delay the onset of the needs analysis phase until until time becomes critical. Vigilant self-evaluation should be a standard procedure during the operational life of a system. An essential factor is maintaining a viable system. In maintaining a viable system is keeping aware of the activities and technology. Varied research and development, or R&D activities, are carried out by many agencies in the industry. They receive support from government or private funding or combinations of both. In the defense sector, contractors are authorized to use a percentage of their revenue on relevant research as allowable overhead. Such activities is called independent research and development, or IRAD. There are a number of wholly or partially government-funded exploratory development efforts. Most large producers of commercial products support extensive applied research and development organizations. In any case, though, the WISE system sponsor or owner or operator should continually keep abreast of these activities and be ready to capitalize on them when the opportunity presents itself. Competition at any level is a potent driver of these activities. Examples of commercial product development may emerge to incorporate features that newer technologies can provide, such as improvements to wireless service, precision location from GPS navigation services, and crowdsourcing of information, such as traffic reporting, product selling, or information providing. Next, let's go ahead and talk about operational objectives. The principal outcome of operational studies is the definition of the objectives. In operational terms, that a new system must meet in order to justify its development. In the needs-driven development, these objectives must overcome such changes in the environment or deficiencies in the current system as have been generated the pressure for an improved system. In a technology-driven development, the objectives must embody a concept of operation, also called a ConOps, that can be related to the important need. The term, quote, objective is used in the place of, quote, requirements because at the early stage of system definition, the later term is inappropriate. It should be anticipated that the interactions would take place before the balance between operational performance and technical risk, costs, and other developmental factors will be finally established. So we get a chance to be seeing some of that here in this figure. Although objectives should be quantifiable and objective, the reality is that most are qualitative and subjective at the early stage. Some rules of thumb can be helpful. Objectives should address the end state of the operational environment or scenario. It focuses on the system, focuses on what the system will accomplish in the large sense. An end state example from the transportation sector may attain a certain behavior from the operational environment, such as an increasing miles per gallon, efficiency, and increasing the renewable energy source infrastructure throughout the nation. Objectives should address the purpose of the system and what constitutes the satisfaction of the need. These would identify qualitative values to determine if the objectives was satisfied or not, such as 1 million metric tons of carbon dioxide removed within a city in a day. Taken together, objective answers, the objectives answer the why question, and why is the system needed. For most objectives, start with the infinitive word provide, but this is not mandatory. Okay, next, in getting into some more of the details, thinking about the objective analysis. The term objective analysis is the process of developing and refining a set of objectives for a system. Typically, the product of the effort is an objective tree where a single or small set of top-level objectives are decomposed into a set of primary and secondary objectives. So we see this in the figure. It illustrates, it shows a decomposition is appropriate until an objective becomes verifiable or you begin to define functions of the system. When this occurs, stop at the objective. The figure illustrates functions by graying the boxes. They would not be part of our objectives tree. In our experience, most objective tree spans 1 or 2 levels deep. There is no need to identify extensive depth. And so I've actually colorized this with a bluish tone, but you can still see the darker and lighter shades on the figure. Well, let's continue on. Now we're going to be thinking about an example of objectives. So an example of objectives analysis, think about a new automobile that can be marketed as a, quote, green or environmentally friendly. Understanding the objectives of the new car establishes priorities for the eventual design. Objectives analysis forces the management and the technical staff to evaluate and decide what is important when developing a new system. Therefore, it is worth investing some time, energy, and capital in determining the overall objectives of the system. Moreover, agreeing to a concise single statement helps focus the development team to the job at hand. If in the automotive example, the company might soon realize that the overall objective of the new vehicle is to provide users with clean transportation. The top level objective does not include performance, cargo capacity, off-road capacity, etc. What is the key overall objectives are 2 keywords, clean and transportation. Both imply various aspects or attributes of the new car. Since both would not yet be well defined, we need to decompose them further. But the overall goal is clear that the vehicle is going to be environmentally clean and provide sufficient transportation. The first decomposition focuses the thinking of the development team. Clearly, the 2 key words need to be fleshed out. In this case, clean may mean good gas mileage as well as comfortable. Transportation also implies a safe and enjoyable experience in the vehicle as it travels from one point to the next. There may also be another objective that is loosely tied to clean and transportation, that is cost. Note that some objectives may not have supporting functions and may not require further decomposition. Generally, all secondary objectives would need to be satisfied before we can claim that it is the primary objective is satisfied. So this is in our example, the development team focuses on 4 primary objectives that flow from our overarching objective: comfort, mileage, safety, and cost. So the figure that we're showing here presents one possibility of the objective tree. We're getting more specific than just those 4 labels. In determining whether an objective needs further decomposition, one should ask a couple of questions. Does the objective stand or on its own in terms of clarity of understanding? Is the objective verifiable? Would decomposition lead to better understanding? Are requirements and functions readily implied by the objective? In our example, one could argue that 3 of the primary objectives are sufficient as stated, and all 3 are verifiable. Only the subjective objective relating to comfort needs to be further decomposed. In this case, comfort can be divided into 3 comfort components: a sound system, noise levels that allow conversation, and physical space. As seen in the figure, these 3 could be all verified by various methods. Satisfaction survey in the first, a definition of noise levels for normal convention, and volume requirements. Having an tree focuses the development effort on the priorities. In our example, the 4 primary objectives communicate what is important with this new automobile. In many cases where objective trees are used, an initial tree will be similar to our example, listing only those objectives that are highest priorities. These trees would then be expanded to include other areas that will need to be addressed. For our automobile, these other areas would include maintenance considerations, human system interaction expectations, and cargo space, to name a few. An objective of having an objectives trees is ultimately to identify the ConUps, the functions, and their performance requirements. Next, let's get into concept of operations. Although the 2 terms are often used synonymously, in truth, an operational concept is a broader description of a capability that encompasses multiple systems. It tends to describe how a large collection of systems will operate. An example would include the operational concept for the U.S. transportation system, or even a subsystem of that whole system. In this case, the system does not refer to a single system, but a collection of family of systems. Another example would be an operational concept of an oil refinery, again, referring to how a collection of systems would operate together. When referring to a single system, the term concepts is generally used. A further distinction relates to scenarios. An operational concept is sufficiently broad to be scenario independent. A ConOps is intended to show how a system concept will work in the operational environment. It is informed by early system engineering artifacts, such as context diagrams that show which system shows which systems, users, or threats the system will operate with, use cases, which cases/conditions and which specific actors, and functional architecture artifacts such as activity or sequence diagrams that the system intends to perform. The ConOps is informed by users by describing the logic or tactics that they intend to employ the system in order to help inform system design by describing how well the system is expected to operate. As the ConOps can be fairly detailed, the description may be limited to a single scenario or a set of related scenarios. Operational concepts are useful since requirements should allow prescribing how they should be fulfilled. Requirements documents risk inadvertently barring an especially favorable solution. However, a set of operational requirements alone is often insufficient to constrain the system solution to the types desired. For example, the operational requirements for defending an airplane against terrorist attacks could conceivably be met by counter weapons, passenger surveillance, or sensory technology. In a particular program initiative, the requirements would be constrained by adding a ConOps, which would describe the general type of counter weapons that will be considered. This extension of operational requirement adds constraints which express the customer's expectation for the anticipated system development. The term ConOps is quite general. The components of a ConOps are mission description with success criteria, relationships with other systems or entities, information sources and destinations, and finally, other relationships or constraints. The ConOps should be considered as an addition to the operational requirement. It defines the general approach, though not a specific implementation to the desired system, thereby eliminating undesired approaches. In this way, the ConOps clarifies the intended goal of the system. The CONOP should be prepared by the customer organization or by an agent of the customer and should be available prior to the beginning of the concept definition phase. Thereafter, it should be a, quote, living document together with operational requirements documents. And so what we're showing here in this figure, we'll get a chance to get exposed to some of this. It provides an overview of the trio of conceptual designs to describe requirements, scenarios, and CONOPs. So all of these are the things that are helpful for establishing the basis for a CONOPs. Okay, next let's talk about scenarios and the hierarchy of scenarios. So a scenario is a description of an operational context, and it is the last piece of the triad of things that in dividing a system concept. So the description is depicted here in the figure that we're showing, and so this just lists the various levels and focuses on the where and when. Specifically, an operational context description describes the environment within which the system is expected to operate. A specific instantiation of the concept is known as a scenario. A scenario can be defined as a sequence of events involving detailed plans of one or more participants and a description of the physical, social, economic, military, and political environment in which these events occur. With respect to system development, the scenarios are typically projected into the future to provide designers and engineers a context for the system description and design. Most scenarios include at least 5 levels. So we have the mission objectives, a description of the overall mission with success criteria. You should notice that this is the same as one of the components of a CONOPS. The mission can be of a type, for example, military, economic, social, or political. Then there's friendly parties, a description of friendly parties and systems and the relationship among those parties and systems. Threat actions and plans, a description of the action and objectives of threat forces. These threats need not be human, they could be natural, for example, a volcanic eruption. 4, there's environmental, a description of the physical environment germane to the mission and system. 5, a sequence of events, a description of individual events along a timeline. These event descriptions should not specify detailed system implementation details. Scenarios come in all sizes and flavors. The type of scenario is determined by the system in question and the problem being addressed. So the figure I'm showing now, it shows the different levels of scenarios that might be needed in a system development effort. During the early phases, that is the needs analysis and concept exploration, the scenarios tend to be higher level, and they're near the top of the pyramid. As the development effort transitions to latter phases, more detail is available as the design improves, and lower level scenarios are used in engineering analysis. High level scenarios continue to be used throughout to estimate the overall system effectiveness as the design matures. In terms of operational scenarios, a logical method of developing operational requirements is to postulate a range of scenarios that together are representative of the full gamut of expected operational situations. These scenarios must be based on an extensive study of the operational environment, discussions with experienced users of the predecessor and similar systems, and a detailed understanding of past experience and demonstrated deficiencies of the current system. It is especially important to establish the user priorities for requirement improvements, in particular those that appear most difficult to achieve. While scenarios range widely in their content, depending on their application, we define 5 basic components of almost all scenarios. First, we have mission objectives. The scenario should identify the overall objective of the mission represented and the purpose and role of the system and focus in accomplishing those objectives. In some cases, the component is system dependent, meaning that the role of any one system is not presented, only a general description of the mission at stake and the objective sought. A commercial example, the mission could be to capture market share. In a government example, the mission might be to provide a set of services to constituents. And in a military example, the mission might be to take control of a particular physical installation. 2, we have architecture. The scenario should identify the basic system architecture involved. This includes a list of systems, organizations, and basic structural information. If government's information is available, this would be included. This component could also include basic information on system interfaces or a description of the information technology infrastructure. In essence, a description of the resources available is provided. In a commercial scenario, the resources of the organization are described. If this is a government scenario, the organizations and agencies involved in the mission are described. If this is a military scenario, these resources could include the units involved and their equipment. 3, for competition, the scenario should identify competition in your efforts. This may be elements that are directly opposed to your mission success, such as software hacker or other types of enemy. This may be your competition in the market or outside forces that influence your customers. This also could include natural disasters such as a tsunami or a hurricane. 4, we have the physical environment. The scenario should identify the environment in which the scenario takes place. This will include the physical environment, for example, the terrain, weather, transportation grid, and energy grid, as well as the business environment, which would include the recession, growth period, stuff like that. So a neutral entities are described in this section. For example, customers and their attributes would be defined, or neutral nations and their resources. The scenario should describe a general sequence of events within the mission context. We are careful to use the term general, though. The scenario should allow for freedom of action on the part of the players. Since we use scenarios to generate operational requirements and estimate system effectiveness, we need the ability to alter various parameters and events within the overall scenario description. Scenarios should not script the system. They are analysis tools, not shackles to restrain the system development. Thus, scenarios typically provide a general sequence of events and leave the details to an analyst using the scenario. At times, the scenario may provide a detailed sequence of events leading up to the point in time whereby the analysis starts and actions may be altered from that time forward. A scenario could include much more depending on its application and intended purpose. They come in all sizes, from a short graphic description of a few pictures to hundreds of pages of text and data. Even though the operational scenarios developed during this phase are frequently not considered a part of the formal operational requirements document, in complex systems, they should be essential inputs to the concept exploration phase. Experience has shown that it is seldom possible to encompass all the operational parameters into a requirements document. Further, the effectiveness analysis process requires operational inputs in scenario form. Accordingly, a set of operational scenarios should be appended to the requirements document, clearly stating that they are representative and not a comprehensive statement of requirements. As noted above, the scenario should include not only the active operational actions of the system with its environment, but also the requirements involved in the transportation, storage, installation, maintenance, and logistics process. These phases often impose physical and environmental constraints and conditions that are more severe than normal operations. The only means for judging whether or not requirements are complete is to be sure that all situations are considered. For example, the range of temperature or humidity of the storage site may drastically affect system life. In terms of scenario development, the scenario development process, there is a simplified process to develop a scenario while it is in the concept development phase. It provides so there is some resources available that can help in this process, and the textbook refers to a template, and so that would be something I'd refer you to the textbook and the resources associated with that. So the textbook provides a template in order to analyze the problem, so it's representative of what you will be using in the real world, as well as ensuring that the relevant topics and issues are addressed. The scenario can be defined as a sequence of events involving detailed plans of one or more participants and a description of the physical, social, economic, military, and political environment in which these events occur. With respect to system development, scenarios are typically projected into the future to provide designers and engineers a context for the system description and design. So scenario development includes the following step. It starts out with defining the mission functions, and mission objectives. This provides a description of the overall mission to include the success criteria. The mission can be of any type, for example, military, economic, social, or political. So each of you, and as you're reading the textbook, should notice that this also will be decomposed to the functional level in terms of describing what is needed to successfully execute the mission. Objectives provide a benchmark to determine when a mission is deemed successful. Next, it defines the friendly parties. This provides a description of the friendly parties and systems and the relationships among those parties and systems. These may either be as is, or that is current, or systems and organizations, or may be identified as to be, looking towards the future, considering the elements at that time. You want to define the threat actions and as well as the plans. This includes a description of the actions and objectives of threat forces that are representative of the either current or future threats activities, and it usually requires some form of official validation of the threat capability. For defense systems, this is usually the intelligence community that provides such validations. For healthcare systems, this could be a consortium of subject matter experts that identifies emerging threats. For environmental systems, these threats need not be human. They could be natural, and so that's a possibility. Then we define the operational environment. This provides a description of the physical and operational environment that the mission will accomplish, and who the system will need to operate with. Next, we define the relevant actions and interfaces. This provides a description of the relevant events along a timeline in order to accomplish the mission. These event descriptions should not specify detailed system implementation details, but rather provide context to match friendly party actions and against threat actions. Scenarios may also be reviewed by operators that are familiar with the mission space to validate the concept being explored, as well as provide insight into current and future challenges to the mission. Okay, we'll finish up this part of the lecture on operational analysis by focusing on two more things, social factors, and then we'll talk briefly about mission analysis. So in terms of social factors, systems may require some evaluation of intended users and how the system may be accepted within the social network and organizational culture. User needs should be explored on how the system is envisioned to perform and interact with the culture, which may require understanding how current and future employees will interact with the system concept. Surveys and interviews, as well as market research from peer companies, may also provide insight on how the system concept may be received. This is of critical importance for systems in global use. The system may be used to enhance relationships between individuals, groups, or institutions as one performs their mission. The textbook refers to a reference from Watson, who examined how systems may influence behavior within the organization, organized into sociological ambivalence that may occur when the organization is confronted with conflicting norms. These may range from conflicts of interest. For example, the employees work in several groups of multiple projects that may conflict with projects or time priorities, to contradicting organizational cultures. And finally, on mission analysis may be performed to evaluate how well the mission can be accomplished using the system concept. It may also be used to evaluate how well the organization and supporting external organization and entities also operate while performing the mission. Mission performance, as well as post-mission sustainment and logistics, may also be a factor to determine how well the system performed and was maintained for the next mission. These may identify additional requirements and interfaces that support the original system, or may motivate additional non-material changes to improve mission performance. Much attention may be paid to the non-material as well as sustainability of system performance, particularly in austere operating conditions. Next, let's discuss feasibility definition. The feasibility of a system concept and therefore meeting the projected need cannot be established solely on the basis of functional design. The issue of feasibility must also address the physical implementation. In particular, system cost is always a dominant consideration, especially as it may compare with the other alternatives, and this cannot be judged at the functional level. Accordingly, even at this initial phase of system development, it is necessary to visualize the physical makeup of the system as it is intended to be produced. It is also necessary to visualize all external constraints and interactions, including compatibility with other systems. While it is necessary to consider the physical implementation of the projected system in the needs analysis phase, this does not imply that any design decisions are made at this time. In particular, no attempt should be made to seek optimum design. Those issues are dealt with much later in the development process. The focus at this point is to establish feasibility to meet a given set of operational objectives. It is the validation of these objectives that is the primary purpose of the needs analysis phase. So the discussion that follows, that correlates to the paragraphs in the textbook, discuss some of the issues that need to be considered, but only at an exploratory way. So first of all, we have the visualization of a subsystem implementation. Given the allocation of functions to subsystems, it is necessary to envision how these might be implemented. At this stage, it is only necessary to find examples of similar functional units in existing systems so that the feasibility of applying the same type of technology to the new system may be assessed. The identification of the principal media involved in each major function, say signal, data, material, and energy, we've already talked about those, is also helpful to find systems with similar functional elements, and hence with physical implementation representative of those required in the new system. We also want to be thinking about the relationship to the current system, where there exists a system that has been meeting the same general need for which the system is intended. There are usually a number of subsystems that may be candidates for incorporation in modified form in the new system. Whether or not they will be utilized as such, they are useful in building a case for system feasibility and for estimating part of the development and production costs of the new system. Existing models and simulations of the current system are especially useful tools in this type of analysis, since they are usually have been verified against data gathered over the life of the system. They may be used to answer what-if questions and find the driving parameters which help to focus the analysis process. Another important tool used in conjunction with the system simulation is the effectiveness model and the analytical techniques of effectiveness analysis. Other less tangible factors can also come into play, such as the existence of a support infrastructure. In the case of automobile engine, many years of successful operation have established a very wide base of support for conventional reciprocating engines in terms of repair sites, parts, suppliers, and public familiarity. Because the prospective cost for changing this base, innovative changes such as the Wankel rotary engine and design based on the Stirling cycle have been resisted. The point here is that the beneficial technological innovations are often overridden by economic or psychological resistance to change. In terms of application of advanced technology, in technology-driven systems, it is more difficult to establish feasibility by reference to existing applications. Instead, it may be necessary to build the case on the basis of theoretical and experimental data available from such research and development work as has been done on the candidate technology. In this case, this provides to be insufficient. Limited prototyping may be required to demonstrate the basic feasibility of the application. Consultation with outside experts may be helpful in adding credibility to the feasibility investigation. Unfortunately, highly touted technical advances may also come with unproven claims and from unreliable sources. Sometimes a particular technology may offer a very substantial gain, but lacks maturity and established knowledge base. In such situations, the case for incorporating the technology should be coupled with a comparably capable backup alternative. System engineers must be intimately involved in the above process to keep the overall system priorities foremost. And then with one other final thing to consider is cost. The assessment of the cost is always an important concern in needs analysis. This task is particularly complicated when there is a mix of old, new, and modified subsystems, components, and parts. Here again, cost models and maintenance records of the current system combined with inflation factors can be helpful. The long-term view is important. By comparing similar components and development activities, cost estimation will at least have a credible base from which to work. In the case of new technology, cost estimates should contain provisions for substantial development and testing prior to the commitment for use. And then as a final topic that we'll cover on this, that we're showcasing as a part of this slide, let's talk about the feasibility of the definition of a feasible concept. To satisfy the objective of a need analysis phase, the above considerations should culminate in the definition and description of a plausible system concept and a well-documented substantiation of its technical feasibility and affordability. The system description should include a discussion of the development process, anticipated risks, general development strategy, design approach, evaluation methods, production issues, and CONOPS. It should also describe how the cost of the system development and production has been assessed. It need not be highly detailed, but should show that all major aspects of system feasibility have been addressed. In order to evaluate the feasibility of this concept, a new product, the operational concept, sometimes referred to as a CONOPS, addresses how and who. To accompany the CONOPS is a description of the operational context that the system will operate with, sometimes referred to as scenarios, and addresses where and when. Okay, for the last major topic we'll cover in this lecture, let's talk about needs validation. So this is the final and most critical step in the application of the system engineering method in the systematic examination of the validity of the results of the previous steps. In this case, of the needs analysis phase, the validation step consists of determining the basic soundness of the case that has been made regarding the existence of a need for a new system and for the feasibility of meeting this need at an affordable cost and an acceptable risk. So let's think about the operational effectiveness model. In the concept development stage, the analyses that are designed to estimate the degree in which the given system concept may be expected to meet a postulated set of operational requirements is called operational effectiveness analysis. It is based on the mathematical model of the operational environment and of the candidate system concept being analyzed. In effectiveness analysis, the operational environment is modeled in terms of a set of scenarios, postulated actions that represent a range of possible encounters to which the system must react. Usually, initial scenarios are selected to present the more likely situations, followed by more advanced cases for testing the limits of the operational requirements. For each scenario, the acceptable responses of the system in terms of operational outcomes are used as evaluation criteria. To animate the engagements between the system model and the scenarios, an effectiveness model is designed with the capability of accepting variable system performance parameters from the system model. Effectiveness analysis must include not only the operational models of the system, but also must represent its non-operational models, such as transportation, storage, installation, maintenance, and logistic support. Collectively, all the significant operational requirements and constraints need to be embodied in operational scenarios and the accompanying documentation of the system environment. Next, in terms of system performance parameters, the inputs from the system model to the effectiveness analysis are values of performance characteristics that define the system's response to its environment. For example, if a radar device needs to sense the presence of an object, say, for example, an aircraft, its predicted sensing parameters are entered to determine the distance at which the object will be detected. It needs to react to the presence of the object, its response processing time will be entered. The effectiveness model ensures that all of the significant operational functions are addressed in constructing the system's model. In terms of measures of effectiveness, to evaluate the results of the effectiveness simulations, a set of criteria are established that identify those characteristics of the system response to the environment that are critical to the operational utility. These are called measures of effectiveness. They should be directly associated with the specific objectives and prioritized according to their relative operational importance. Measures of effectiveness, or MOEs, and performance are described later in the requirements analysis. While the effort required to develop an adequate effectiveness model for a major system is expensive, Once developed, it will be valuable throughout the life of the system, including potential future updates. In the majority of cases where there is a current system, much of the new effectiveness model may be derived from its predecessor. Well, let's explore the analysis pyramid. When estimating or measuring the effectiveness of a system, the analyst must need to determine the perspective within which the system's effectiveness will be described. For example, the system effectiveness may be described within a larger context or mission where the system is one of many, working loosely or tightly coupled together to accomplish a result. On the other hand, effectiveness can be described in terms of the individual system's performance in a given situation in response to selected stimuli where interactions with other systems is minimal. So we're showing here in the figure a depiction of a common representation of what is known as the analysis pyramid. At the base of the pyramid is a foundational physics and physical phenomenology knowledge. Analysis at this end of the spectrum involve detailed evaluations of environmental interactions, sometimes down to the molecular level. As the analyst travels up the pyramid, details are abstracted and the perspective of the analyst broadens until he reaches the apex. At this level, technical details have been completely abstracted and the analysis focuses on strategy and policy alternatives and implications. The systems engineer will find that typically analysis perspectives during the needs analysis phase tend to be near the top of the pyramid. Although the strategy may not be the domain of the system development effort, certainly the system's effectiveness within a multiple mission or single mission context would need to be explored. The lower part of the pyramid is usually not analyzed due to the lack of system definition. As a system becomes more defined, the analysis performed will tend to migrate down the pyramid. We'll explore the analysis pyramid more as we continue our look at the system engineering within the development phases. Okay, in terms of the validation of feasibility and need, finally, the effectiveness analysis described above is mainly directed to determine whether or not a system concept derived in the functional and physical definition process is one, feasible, and two, satisfies the operational objectives required to meet a projected need. It assumes that the legitimacy of the need has been established previously. This assumption is not always a reasonable one, especially in the case of technology-driven system development, where the potential application is new and its acceptance depends on many intangible factors. Case in point, of which there are hundreds of examples, the application of automation to a system previously operated mainly by people. The airplane reservation and ticketing system is one of the larger successful ones. The validation of needs for such a system requires technical, operational, and market analysis that seeks to take into account the many complex factors likely to affect the acceptability of the automation system and its probable profitability. In complex cases such as the above example, only a very preliminary validation can be expected before considerable exploration, development, and experimentation should take place. However, even in a preliminary validation analysis will bring out most of the critical issues and may occasionally reveal that the likelihood of meeting some postulated needs may be too problematic to warrant a major investment in the current state of the technology. The primary product of need analysis is a set of operational objectives, which are then translated into a set of operational requirements. The system operational requirements that result from the needs analysis phase will establish the reference against which the subsequent development of the system to meet the projected needs will be judged. Accordingly, it is essential that these requirements be clear, complete, consistent, and feasible of accomplishment. The feasibility has presumably been established by the identification of at least one system approach that is judged to be both feasible and capable of meeting the need. It remains to be certain that the operational requirements are adequate and consistent. In terms of feasibility validation, effectiveness analysis is intrinsically concerned with functional performance of a system and therefore cannot in itself validate the feasibility of the physical implementation. This is especially true in the case where unproven technology is invoked to achieve certain performance attributes. An indirect approach to feasibility validation is to build a convincing case by analogy with already demonstrated applications of the projected technique. Such an approach may be adequate provided that the application cited is truly representative of the proposed in a new system. It is important, however, that the comparison be quantitative rather than only qualitative, so as to support the assumed performance resulting from the technology application. A direct approach to validating the feasibility of a new physical implementation is to conduct experimental investigation of the technique to be applied to demonstrate that the predicted performance characteristics can be achieved in practice. This approach is often referred to as the critical experiments, which are conducted early in the program to explore new implementation concepts. The resources available for carrying out the validation process in the needs analysis phase are likely to be quite limited, since the commitment to initiate the actual development of the system has not yet been made. Accordingly, the quality of the validation process will depend critically on the experience and ingenuity of the system engineering staff. The experience factor is especially important here because of the dependence of the work on knowledge of the operational environment of the predecessor system, of analysis and studies previously performed of the technological base and of the methods of system analysis and systems engineering. And finally, the importance of feasibility demonstration in defining a basis for developing a new system. The needs analysis phase not only demonstrates the existence of an important unfulfilled operational need, but also provides evidence that satisfying the need is feasible. Such evidence is obtained by visualizing a realistic system concept that has the characteristics required to meet the operational objectives. This process illustrates a basic system engineering principle that establishing realistic system requirements must include the simultaneous consideration of a system concept that could meet those requirements. This principle contradicts the widely held notion that requirements derived from needs should be established prior to consideration of a system concept that can fulfill those requirements. Here is a summary of what we've talked about in a fairly quick fashion. First of all, we considered originating a new system. Objectives of a new analysis phase are to identify a valid operational need for a new system and develop a feasible approach to meet that need. The needs-driven system development approach is characteristic of most defense and other government programs and typically stems from a deficiency in current system capabilities. This type of development requires a feasibility and affordability technical approach. The other major type of approach is a technology-driven system development approach. This approach is often characteristic of most commercial system developments and stems from a major technological opportunity to better meet a need. This type of development requires demonstration of practicality and marketability. Activities comprising these needs analysis phases are operation analysis, understanding needs for a new system, functional analysis, deriving functional requirements to accomplish operations, feasibility definition, visualizing a feasible implementation approach, and needs validation, demonstrating cost effectiveness. For system thinking analyze the systems from a holistic perspective to consider the entire operational and physical environment. This is done to identify what other systems and organizations will influence a system when determining the initial needs. Operational analysis. Studies and analysis are conducted to generate and understand the operational needs of the system. These studies feed the development of an objective tree describing the hierarchy of system expectations and outcomes. Development of ConOps scenarios and mission statements, as well as incorporating social and technology views, are critical to succeed. Feasibility definition. The system development approach is decided upon, articulated to stakeholders, and appropriately costed. Moreover, an early feasibility system concept is articulated. Finally, developing operational requirements commences. And the last item here is needs validation. The vetted set of operational needs is now validated by operational effectiveness analysis, usually at multiple levels within the analysis pyramid. System concepts which satisfy the operational needs are evaluated, use agreed upon measures of effectiveness, MOEs, and reflect the entire system lifecycle. All right, well, thank you very much. That's it.